All right, so this is Taylor Polynomials 9.2 in the textbook. So this is Taylor Polynomials. So we just did power series, right? And power series should make sense. I ignore all of this. This is me trying to understand what the hell is going on, and try to find a good way to represent everything. Don't worry about this yet. But anyway, this is a very big chapter because there's remainder theorems and all of that. So you might see a cut in this video, or I might just upload this video first and then the second part, because I spent like 2 hours, I don't know, like an hour and a half learning like 6 pages, and I really don't feel like learning another 3 pages of remainder theorem and spending another like half hour on that, right? So I figure I'm just gonna, do my spiel on Taylor polynomials thus far. All right, so before we dive into Taylor polynomials, right? Or actually, yeah, let's define what a Taylor polynomial is in just words. A Taylor polynomial, so you have a function, right? I'd say it's a pretty complex function, like, okay, that's a bad function, like this maybe. Maybe like a, right? Let's say we want a Taylor polynomial at this point. What a Taylor polynomial is it has a certain degree, all right? And the higher the degree, the closer it will be to this entire function. All right, for example, a degree 1 Taylor polynomial is probably just like the tangent line at this point, right? Like not an amazing, it's not amazing, right? I mean, it's better than the degree 0, which I believe is just this, right? That's degree 0. But degree 1, it'd be like a tangent line, okay? And in degree 2, we would have like a parabola. Maybe it looks like this, right? Like it's okay. It's not too bad. And then maybe degree 3, it looks like this, right? It's okay. It's getting closer, right? These are what Taylor polynomials are. They allow us to approximate complex functions using just polynomials, because Taylor polynomials are always in the form of some power series. Right? Like some ck and x minus a to the k, right? It's in this form, something like this, all right? So like a Taylor polynomial could be like x plus x squared plus x cubed over 8 or something like that, right? So we want a good approximation. This is what Taylor polynomials are meant to do. So to investigate what approximation means, let's take a look at these two. All right. We want to approximate f at x. All right. It's just a straight line. All right. It's just worry about the straight line as n goes to infinity. All right. We want to see which one's a better approximation. And the way we can measure approximation is trying to find the difference between two functions at some point, right? Like, for example, like for this function, right? We could say green is closer to black more than red is closer to black, right? And that is what we call remainder, right? I know, crazy stuff. This is remainder. And the difference between these two functions, they both approach f at x. All right, let's assume g at x asymptotes towards f at x, yeah? But clearly, p of x is a better approximation of f at x, even as n goes to infinity, right? Like p at x is always closer, or like it's kind of there, right? Now, how do we know, right? What does this mean? Like, how do we define that p at x goes to f at x faster, right? That seems like a weird concept because g at x still goes to f at x, right? So this is where I want to introduce some ideas. If we define the remainder, let's call it r at x, all right, is equal to f at x minus p of x. Okay, this is the remainder. So this is like it's like at this point it's this much, at this point it's this much, at this point it's this much, right? We're going smaller and smaller and smaller, right? So obviously this guy, the limit as x goes to infinity of r at x is going to be 0, right? That's pretty obvious. But That's the case for g of x too, right? If we define r2 of x is equal to f of x minus g of x, this also is the same. So how do we know that this one is a better approximation? Well, we want to see that its limit approaches 0 faster, right? All right, so now I'm not going to use g of x anymore. All right, I'm going to use something else. I'm going to use something in the form of like 1 over x. All right, because 1 over x, okay, let's assume all of these, for simplicity, all of this is going towards 0, yeah? And if we compare it to 1 of x, right? Say r at x is a better approximation for f at x is equal to 0 than 1 over x is. All right, so what does that mean? That means if we divide the remainders, right, r at x divided by 1 over x as the limit goes to infinity, right, this should equal 0, right? Because if you think about it, right, this guy is going to 0 fast. Yeah, he has to be going faster than this guy. So this guy should be 0, right? R at x, or which is equal, let's write this at f at x minus p at x, right? Let's assume g of x is 1 over x. All right, that's not what 1 over x looks like, but let's assume on some interval that it looks like that, right? Obviously, p of x is a better approximation. So when we divide the two, this should equal 0, right? This is the idea. We can also write it like this. Maybe this will be a bit more clear. All of this times x, right? Obviously, x is going to infinity, right? You can see these two are equal, right? We just, rewrote this. X is going to infinity, but for this limit to equal 0, this guy has to be approaching 0 faster than x is going to infinity, right? So that's sort of the idea of these remainders. And, well, we invested the case as x goes to infinity. But for Taylor polynomials, we're not exactly interested in infinity. In fact, I don't think we can even use Taylor polynomials for like x goes to infinity. We want to generalize this as x approaches some number a. But the same idea holds, right? So if we take a look at the equivalent statement as the limit as x approaches a, right? Let's have a different function now. Let's have different functions. Let's have cos. Let's have cos, right? If we want to approximate cos at 0, right? Or at some a, at some point a. This would be a cos a. Yeah? We want to see the limit as x approaches a, right, of f at x minus p of x over x minus a to some degree. All right, let's call it n. All right? And this has to equal 0. This logic should follow. So we have as x goes to infinity. That one makes sense, right? This one probably makes a bit less sense, right? Because now we've replaced it with this. But keep in mind, this is just saying it's faster than some degree, right? Because with this one, right, we could have said this was faster than x squared as well, right? And as you can see, if you increase its degree, right, 100, then this guy's a damn good approximation, right? Because as x goes to infinity, this guy goes infinity, like crazy infinity, right? This guy's like infinity, like a million, right? A million infinities. But this guy still beats him, right? This guy still approaches 0 fast enough, right? That's the same idea here, right? In fact, except that it's now approaching 0. This bottom is approaching 0, right? But you gotta approach 0 faster than this guy. Another way we can write this out that might make it a bit more clear is writing f at x minus p of x times 1 over x minus a to the n equals 0. This guy goes to infinity, right? Especially if n, let's say n was like 100, right? Then as x goes to a, this guy goes to 0, and that little term is being amplified by this 100, right? So this should be infinity. But if this guy still beats him and equals 0, then this guy's a damn good approximation, right? So this is sort of what we're saying. And we say that a polynomial, or a Taylor polynomial, which is p, by the way, or sorry, so when we say P is a good approximation, right, of some order, that's corresponding to what this n is. We can write P sub n, right? And this has to hold for any Pn that we define as an approximation of order n. Prox of order n, right? This is the definition. For P sub n of x to be a good approximation for f of order n, right, then this limit has to hold. Let's investigate another property of this. Okay, so we know this is true, right? And also, we know this top term has to equal 0 for this to be true, right? Otherwise, let's say it wasn't 0, then it wouldn't equal 0, right? So we know that f at x minus p sub n of x has to equal 0, meaning actually f at x has to f at x has to equal p sub n of x, right? But this is only at the point of a. Sorry, yeah, that's a big distinction. It has to be true at a, right? Otherwise, this limit wouldn't go to 0. Does that make sense? Like that should make sense, right? Now we can use L'Hopital's rule and say this is after LH. X goes to a of f prime, right? We're just differentiating, right? And this is n x minus a of n minus 1 equals 0. And now we agree that this also has to equal 0, right? Otherwise, this limit wouldn't equal 0. So what we see is that f prime at a minus pn of a prime equals 0, right? Meaning we get this chain of equalities. We have f at a is equal to pn of a, right? F prime at a has to be equal to p prime of n of a, right? All the way up until f to the nth prime has to be equal to the p of the nth prime at a. These all have to hold for some, these have to hold for some approximation, p sub n of a, at x, for f at x. And this and this are equivalent definitions for approximation, okay? And therefore Taylor polynomial, okay? These are like definitions for Taylor polynomial. Not definitions that are exclusive to Taylor polynomials, but these are properties that Taylor polynomials must agree with, because these are just like approximations, right? This is like this is saying the approximation is quite good. This is saying the approximation is quite good up to n. To illustrate this further, let's instantiate with this. Let's take a look at this. All right. What we want to show is that this is true, right? And first we assume that this limit is true. So we assume that it's a good approximation up to order 3 at 2, right? So let's say f at x is like it's like this, right? We're saying at 2, at x equals 2, this is a good approximation up to order 3. So maybe the approximation looks like something like this, like 2, 3. Right, maybe it looks like that, right? Now, what does that mean? Well, let's take L'Hopital's rule, right? L'Hopital's rule means that f prime at x minus p prime at x over 3x minus 2 to the 2 has to equal 0. Okay, and then now we do it again, right? This becomes 6x to the minus 2 equals 0. All right, let's do it again. One last time. And the bottom just cancels out to 6, right? And the top we have triple prime. Now, for this one especially, you should be convinced that f triple prime at 2 has to equal p triple prime at 2, right? Otherwise, this would not equal 0. This limit wouldn't equal 0. right? And this is also supposing these are continuous functions, right? If they're not continuous, I think we run into issues. In fact, what do we... Okay, I don't know what happens when they're not continuous. Let's just assume they're continuous, right? I don't think we're gonna work with functions that are continuous. But since this is 0, right, then we know this also has to equal 0, the top here, as x approaches 2. So then we get this chain of inequalities that we wanted, right? All right. So that was a lot of yap. But now let's actually do something with it, yeah? All right. So now let's find a general formula for Pn of x, all right? And let's write it as let's write it as a power series, because we know we want power series, right? Power series is something we can work with. So we can write it as like let's say like C0 plus C1 x minus a plus C2 x minus a squared plus blah, blah, blah to Cn x minus a to the n, okay? This is what we want. Now, this is the very key part, because we know for any k, it would be k less than or equal to n. For every k, right, we have p to the kth prime at a is equal to f to the kth prime at a, okay? This is a very important fact. This is what we proved earlier. I erased it, but like, this is what we proved earlier. And this is very important, because now we can see p prime n of k is equal to C1, right? This gets is like demolished, right? And this guy turns into just C1. And then we have C2 x minus a, blah, 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 right? And if we take a look at these guys at x equals a, we see that this guy cancels out, this guy cancels out. Sorry, hold on. This guy cancels out, this guy cancels out, all of these guys cancel out. And for this one, this guy cancels out, and all the other guys also cancel out. In other words, we can see a certain formula for these c's. I'll do it one more time with the next one. P double prime of n. We would see that if we take the double prime. Okay, let me get rid of these. Like, C3. Let's see. This would be this next one would be 6c3 of x minus a squared, right? And the double prime would be 2c2 plus 12c3 x minus a plus blah, blah, blah. And these cancels out when x equals equal to a, right? This means we have this formula. We have f at a, right, is equal to pk of a. But we know this is just equal to something about ck, right? C0, C1, C2, right? But there's a bit more to it, because we also multiply by some constant sometimes, right? Like here we turn to a 2, right? And the pattern we see is hold on, something went wrong up here. Oh, sorry, this is meant to be a 3. The pattern we see is something to do with factorials, because if we take, let's say, x to the 4, right? When we take the derivative 4 times, we get 4x3, 12x2, 24x, and then 24. 24 is equal to 4 times 3 times 2 times 1, right? And this is equal to 4 factorial. So we see that we can actually write k factorial in front of this bad boy. And now we get a term for c. Fk at a is equal to over k factorial, right? Hopefully this derivation made kind of sense. So now we can write our power series, right? Well, we we defined pk, pn of x, as the sum from k equal to 0 to n of ck times x minus a to the k. That's the same thing up here. And now we know what ck is. Boom. This is our general formula for a Taylor polynomial. Pretty cool, eh? Okay. So now, let's do some quick notation. This Pn, right, we will call the nth Taylor polynomial at A for f, okay? That's what we define this as. And now, that was page 1, by the way. You should be familiar with the Maclaurin series from Alfonso, right? I mean, every time I'll refer to them, I'll, write them down for you. But now we get into some really weird properties. Oh, not weird, really cool properties, but are kind of confusing as well. Let's do this one first. Let's determine the nth Taylor polynomial for f at x is equal to 1 over 1 minus x at a is equal to 0. Right? And we know this intuitively. This is the geometric series, right? So this is obviously probably something like maybe like n in the case of zeros, like x to the k, right? This is probably where it's going to head, because this is the geometric series. This is what the geometric series is given by. This is something like this we're expecting, right? So now we'll know we got to it if that's the case. Okay. Now let's actually see how we can solve it. So we know the Taylor polynomial is given by this, right? The sum of n k is equal to 0 to f at k time at 0, right? Divided by k factorial times x to k, right? This should make sense. So now we need to see if we can rewrite f prime of k at 0 as something in relation to k. Because if we were able to do that, then we can replace this term with some constant, and then we'll be good. So let's investigate that. Feel free to do this on your own first, and then see if you got the same answer as me. Nothing about this should be too new. If you've watched Alfonso and you just listened to everything I just said, and I was okay explaining, this should make sense. So let's take a look at this. F at x is equal to 1 over 1 minus x, right? Now f prime at x, if we differentiate this guy, right, we'll end up with 1 over 1 minus x squared, right? Because we'll have a negative 1, and then that negative 1 is chain ruled by this guy to cancel out back to positive. And then now we know double prime at x. Okay, we bring the 2. This is also the same as saying 1 minus x to the negative 2, right? So there's a negative, but then this chain rule negative cancels out. So this becomes 1 minus x to the cube, right? F triple prime. We have 6. You can confirm these. This is all true. And now we see at the kth derivative, right, we have k factorial over, this would be 1 minus x to the k plus 1, right? If you can see the pattern. And so therefore, fk at 0 would be k factorial over an x to 0, so this is just 1 to the k plus 1, this is just nothing. So this is equal to k factorial. Okay, great. So now we can rewrite this. K is equal to 0. We have k factorial over k factorial times x to k. This cancels out, and now look at that. We got our geometric series. Beautiful. All right, so for this example, we'll do the same thing, except instead of finding a general Taylor polynomial of degree n, we'll find one specifically for the third order. So let's find the third order Taylor polynomial of f at x, which is equal to the ln of the absolute value of x squared minus 2 at a equals 1. Okay, so now we want to find this polynomial, right? This is all fine and dandy. We have this is a finite sum, by the way, and this is f prime of k at 1, right, over k factorial times x minus 1 to the k. Great. So now we'll do the same thing, except we don't actually have to find a general formula for f prime k at 1. We can just find them like manually, right? So let's take a look at what f at 1 actually is. F at 1 is just 0, right? Because f at 1, this guy will become -1, right? All this guy will become -1. And then ln of 1 is 0, right? That should make sense. Now let's take a look at f prime at x. F prime at x is equal to 2x over x squared minus 2, right? This should make sense. And so yeah, okay. And then when we plug in 1, we end up with -2, right? Great. And now the second derivative. Okay, and to solve for this, we have to quotient rule this, which is great. There we get 2 times x squared minus 2 minus 2x multiply this x squared minus 2. Or sorry, the derivative of x squared minus 2, which is just what, 2x squared. And this is all over x squared minus 2 squared. Now what do we have? Now this f double prime at 1 is equal to -2 minus 4 over 1, right? And this is -6. Okay. Okay. All right. Next one. F triple prime. Okay. I mean, I'm sure the book is right. I'm just gonna copy what the book has. 4x x squared plus 6 over x squared minus 2 to the 3, right? And then the book allegedly says f triple prime at 1 is -28. Great. Okay. These are the values. So this is what we did manually, right? With the help, well, I did with the help of the book. You can probably do it on your own, but I don't really want to do that. So we can rewrite this and just, you know, open the sum, right? So that's 0. This is all 0. So 0, there's no term, right? And then at 1, k is equal to 1, we have -2 times 2 factorials 4 over x minus 1, right? Or sorry, k is equal to 1. Sorry, this is just x minus 1. And then next term, we have k is equal to 2, right? So we have -6, and then this should be over 2, right? So this will be x minus 1 squared over 2, right? And then, hold on, let me move this to the side. I don't have enough room here. And then when k is equal to 3, we have -28 times x minus 1 cubed over, this would be 3 factorial, which is 6. Right, so then we end up with -2 x minus 1, Whoops. Minus 3x minus 1 squared minus 14 over 3x minus 1 cubed. And boom, that's the answer. So, let's see. Now I'm going to introduce some properties of Taylor polynomials. First, let's have this notation just for ease of use. This means Taylor polynomial of order n of f at a. Okay? And so we know a few things. Sorry, hold on. This should be the other way around. My bad. We know that it is linear. So what does that mean? Okay, so that means for f plus g, right? This is equal to a n f, a bit of linear algebra for you, right? Same with, it's also, what's it called? Closed under scalar multiplication, right? We know this. We can integrate it. All right, so we know this is equal to this. And we can also, differentiate it, and then we can also integrate it. This would be, Tan of f, and then I guess plus c. And then this is the one I'm going to spend a lot of time on, because there are some subtleties to it. But we know this. It's also, I don't know the term, multiplicative. I don't know. But say we have this, right? This is equal to Tan of f times Tan of g. However, this can only at most be degree n. And I'll demonstrate in some examples, right? Because it's kind of hard to do it without examples. But okay, these are the properties we know. Okay, that's all fine and dandy. Put those guys over there. Now the example I want to look at. So we know all of this, and keep in mind, the Maclaurin series, right? Let's figure out the Taylor polynomial. Actually, I'll give an example of what I just meant by highest degree n. Let's take the Taylor polynomial of e to the x times e to the x, okay? Let's say we want to do that. Taylor polynomial a of n over e to the x times e to the x, okay? So this would be equal, let's say the third one. The third Taylor polynomial centered at 0. At e, 0. Let's do 0. Okay, so we know this is equal to 0.3 of e to the x times t0.3. Keep in mind, this is a very easy example, and you probably could do it without even using this, but I just want to illustrate what I mean. So we can rewrite this as the Maclaurin series, right? And this would be Maclaurin series is x to the k over k factorial. And this is all multiplied by 3k equals 0 to this, right? And we can see this is equal to 1 plus x squared over 2 plus x cubed over 6, right? This is all times by 1 plus x cubed over 2 plus x, this, right? Notice how our degree is 3, right? But when we multiply all of this together, we'll have blah, 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 and then something x to the 4 over blah, 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 plus x to the 5 over blah, blah, blah. So what I mean is that for all these terms, we don't include them. And this is because when we get to the higher orders, we start to lose our accuracy. Because we only know this is true for up to order 3, right? And we multiply it by something that's also up to order 3. When you multiply those together, right? Would you agree? Okay, let's take a look at this graph. Let's say we want to approximate this, right? If we have some order 3 approximation there, right? And let's say we have another order 3 approximation here. Order 3. So when we end up getting like some order, I guess it'd be order 6, right? Our product would be order 6 because we end up multiplying these two terms together at the very end, right? We cannot say this is an approximation for order 6 because we're not accurate up to order 6. Notice how we're so inaccurate after order 3, right? Okay, order 3 up to like this over here, beautiful. Very good approximation. But over here, we're very bad, right? So we can't claim that we can actually go up to order 6. We can only go up to order 3 right here, right? So that's what I mean. And here's how you can take a lot of shortcuts in computation. So if we were to do this, right, we would end up multiplying 1 by 1, okay, plus x, right, plus x squared over 2 plus x cubed over 6, right? Okay, beautiful. And now we go to the second term. So plus x squared plus x cubed over 2. But notice how if we were to multiply the next one, right, this guy we will end up discarding anyway because we can't assume that he's accurate up to order 4. So we can just not even do that calculation. And same with the next term, plus x squared over 2 plus x cubed over 2. We don't have to keep on going. And finally, for the last term, we can just add the single one, right? Because we know as soon as we go to the next one, it'll be inaccurate. And then we simplify this, and then we get our answer. That's what I mean that we go up to the highest order. So now let's illustrate this with an example. And you can do this example with me. F at x, or on your own, is sin x times e to the x. Let's find the fourth killer polynomial centered at 0. So this would be 4 at 0 of f. I'll let you do it on your own and come back, knowing everything we just said. Okay, so let's define, so we can write this as t of 4, 0 of sin x times t 4, 0 of e to the x, yeah? This all tracks. And then now we can write this as a sum to 4 k is equal to 0 of, it would be 1 to the k, is it k, or I know this is x 2k plus 1 over 2k plus 1 factorial. Is it negative 1 to the k? It is negative 1 to the k, okay. And then this is multiplied by 4k is equal to 0 of x to the k over k factorial, yeah? Okay, this is good so far. And now if we write this out, this is another reason why this is it's nice that you can just ignore the higher degrees. Because when we expand this out, right? Okay, so the first k is equal to 0, we have everything is, that's 1, it's just x, right? And then k is equal to 1, we have minus x cubed over 6, right? When we go to k is equal to 2, right? Notice that we would get x to the 5 over 120. This is already over our limit of 4. So we can just straight up just write that only. Just write these two terms. Because every other term we add after is going to end up inaccurate. Because keep in mind that no matter what you multiply x to the 5 by, right, for any non-negative exponent, this is still going to be degree 5, right? So we don't include him. And now for this one, it's just 1 plus x squared over 2 plus x3 over 6 plus x... Oh, and this is another one. We could include x4 over 24, right? We could. But as soon as we expand him out with this, he becomes an order that we'll end up discarding anyway. So we can actually get rid of him too. You don't have to. I mean, if you want to play it safe, you can just get rid of the terms after. But this saves a lot of time. And now when we multiply this out, right? X squared plus x cubed over 2 plus x4 over 6 minus x cubed over 6 minus x4 over 6. Notice how we don't keep on going. If we were to keep on going, this degree would be 5. And we get it too much. It's too much. So we stop here. And now we can collect like terms, right? We see that these guys cancel out, and we're left with 2 over 2 minus over 6. That's plus 1 over 3. Boom. This is our Taylor polynomial up to degree 4, right? Notice our degree 4 things canceled out, right? That's how we do it, okay? This is yeah. Okay, great. And now, okay, that one's kind of stupid. I might skip that one. Yeah, I'm gonna skip that one. I don't think they'll test that. Okay. And now, lastly, I want to teach you this strategy. And this is so we just did multiplication, right? Now, what if we wanted to do something like tan x, right? To do tan x, we have to divide sin by cos, right? But, I mean, so isn't this just the same as dividing? Well, not exactly. You can't, because if you end up dividing, you'll get something like 1 plus 6x squared over, like, or like x, this is like 3. So you get something like x plus 6 to the 3 over 1 plus x squared, right? This isn't a Taylor polynomial. Like, it's accurate, right? And this is a very good approximation. But it's not a Taylor polynomial. So what do we do? I'm going to go through one of his examples because it's not very intuitive, all right? And then I'm going to give you another example. That's not even in the textbook, by the way. I'll get ChatGPT to verify my answer once I solve it. But essentially, I'll just run through this example and then you'll do the next example on your own. So don't try this yet. It's not very intuitive unless you're like confident that you can get it. All right. So let's rewrite tan as this. Okay, sorry. I should define more of the question. We want the third Taylor polynomial when a is equal to 0. Okay. So then we want 3, 0. This would be tan x is equal to sin over cos. Well, we can write that as, okay, sin is great. But then let's get cos to both sides because we know cos x tan x is equal to sin x, right? Because we just end up canceling out this term, right? So let's write that. And remember, the Taylor polynomial we want for tan x, right, is in the form of a0 plus a1 times x plus a2 times x squared plus a3 times x cubed. That's what we want eventually, okay? And so we can literally plug that into here and solve for that system of equations. So sin x, would you agree that this is just x minus x cubed over whatever, like x cubed over 6, right? And then cos x is just 1 minus x squared over 2. And then we can plug in our a's. So a0 plus a1x plus a2x squared plus a3x cubed, right? And now let's expand the left side. a0 plus a1x plus a2x squared plus a3x cubed minus a0 over 2x squared minus a2 over, a1 over 2x cubed. And keep in mind, we don't keep on going, right? We only want up to degree 3. So we only care about the terms that are degree 3. And now you might be like, what the hell do we do? Okay. But for these polynomials, when we're solving these polynomials, we can write this as 0 plus x plus 0 times x squared minus x cubed over 6, right? And once we collect all like terms, so x has only one term plus, and then a2 minus a0 over 2 x squared plus this would be a3 minus a1 over 2 x cubed, right? So we're just collecting like terms. We know that this must equal here, this must equal here, this must equal here, and this must equal here, right? This is how we solve systems of polynomials. Okay, so this is pretty easy. So we know a0 is equal to 0, obviously. a1 has to be equal 1, right? a2 minus a0 over 2 has to equal 0, right? Since a0 equals 0, then we know this is a2 equals 0, right? And then a3 minus a1 over 2 has to equal negative 1 over 6, right? And this one, we know a1 is 1, right? So we have a3 minus 1/2 is equal to negative 1 over 6, right? And then we have a3 is equal to 1/3, right? And now, boom, we have all the variables we need for our Taylor polynomial. Therefore, we know the Taylor polynomial of tan x is equal to a0 is 0, right? So we don't write a0. a1 is 1, so we have x. a0 is 0, right? But then a3 is 1/3, so we have plus 1 over 3 x cubed. And that's how you do it. Boom, done. Now, so this is how you do it. Now I'm going to give you a problem, right? And I'm going to solve it like literally right now, right? The Taylor polynomial, let's say the third Taylor polynomial at x is equal, a is equal to 0 of, let's do this function. Let's do 1 minus x e to the x. And yeah, good luck. I'm going to do it right now, though. Okay, so what we should see is that we have two series. We have e to the x, and we have 1 over 1 minus x. And basically what we did was divided this one by this one. All right. So now we can rewrite this series. So we can, let's write this out. Of 1 minus x e to the x. We can write this as 30 of e to the x divided by, so let's move to the other side, of 1 over 1 minus x, right? And note that these are just this one, where we know we can write as, it'd be 1 plus x squared over 2 plus x cubed over 6. And on the left is just 1 plus x squared plus x cubed, right? And here we have a0 plus a1x plus a2x squared plus a3x cubed. All right, now let's expand it out. So this side remains the same. And we have a0 plus a1x plus a2x squared plus a3x cubed plus a0x plus a1x squared. This is going to be long. Hold on. a2x cubed plus a0x squared plus a1x cubed plus a0x cubed. Okay? And now we can combine like terms. Sorry, I chose like a really crappy function for this one. But it is what it is. Let's take all the like terms of the low. So it becomes a0 plus, and then x has a1 plus a0, x plus, and then x squared has a2 plus a1 plus a0. And then x cubed has a3 plus a2 plus a1 plus a0. Okay, so we know a0 has to equal 1. a1 plus a0 has to equal 1, right? But since a is 1, that means a0 is 1. So that means a1 is equal to 0, right? We know a2 plus a1 plus a0 has to be equal to 1/2, right? Since we know a1 is 0, that means a2 has to equal negative 1/2, right? And then now finally, a3 plus a2 plus a1 plus a0 has to equal 1/6. And so we know, let's see, a1 is 0, this is 1, negative 1/2, a3 is equal to 1/6. And so we have a3 is equal to 1/6 minus 1/2, which is negative 1/3. And now we have all our a's. So now we can write this of 1 minus x e to the x as 1 minus 1/2 x squared minus 1/3 x cubed. And yeah, I believe that's it for this half chapter. And then next up is the remainder theorem, which I haven't learned yet. I'm about to learn it probably tonight. I think I'll have this video that video separate from this one though, because there's so much content. But yeah, that's Taylor Polynomials. Enjoy.